This video is all about chirality. So, for a carbon to be considered chiral, you have to have all four groups attached to it to be unique. So when we're talking about whether or not the chain coming off of the carbon is unique, we have to consider the entire chain, not just what is directly connected to the carbon. And we'll see some examples in a moment. Also, carbons that have more than one hydrogen are automatically what we call achiral, and that's just the opposite of chirality, so not chiral. Another type of carbon, which I did not include here, so please add this to your notes, is that a carbon that has a double or a triple bond is also achiral. Okay, so anytime that a carbon has multiple hydrogens or has a double bond, it's automatically achiral because it's not going to have four unique groups, and with double or triple bonds, it's not even going to have four groups. It's only going to have three or even two. Okay, so let's look at what this means. If I'm looking at a structure and I'm trying to determine all the chiral carbons, the first thing I'm going to do is go through and eliminate all of the automatically achiral carbons that I can spot. Those are the ones that have multiple hydrogens or that have double or triple bonds. So, as I'm looking at this first structure, the carbons on the end have 3 hydrogens, so those can't be chiral. This carbon has 2 hydrogens, as well as this one and this one, 2 hydrogens, 3 hydrogens, and 3 hydrogens on those. So all of those are automatically eliminated just because of the number of hydrogens. I can also eliminate this carbon because it has a double bond. Okay, so there's only 3 possibilities to even have chiral carbons. So we're going to look at this first carbon on the left, and here's where it would help to have a pencil for questions like this, because I'm going to have to constantly go through and circle and then erase as I check each carbon. So if I want to check this carbon on the left, I need to check all the groups around it. And so it helps to circle. You have a carbon chain, a 2-carbon chain coming off the top. There's a CH3 off on the left. And then on the right, we have this entire structure. Okay, so I am asking if those 3 circled things, are they all unique? Are they all different? And they are, right? The top has 2 carbons, the left has 1 carbon, and the right has a whole bunch of carbons. So those are unique, and then the 4th unique group, of course, is that hydrogen. So if we have 4 unique groups, then the carbon connected to all 4 of those groups is considered chiral. And so I'm going to put a star right there on that carbon. Okay, now we're going to check this middle carbon. And again, we want to check the 3 groups that are attached on the left, right, and top. And I'm asking, are those 3 circled groups, are they unique? And they are, because the top is just a single carbon, and then the left and the right are different. You can tell based on that double bond. The right-hand side has a double bond in it. Okay, so because those 3 groups are unique, we're also going to put a star on that middle carbon. Okay, and then the last one we're going to check is this carbon on the far right. We're going to circle each group that's connected. And here you can see that these 2 groups are not unique. They're both CH3 groups. Okay, so because it's not unique, that is also achiral, and we can mark it out. So I only have 2 chiral carbons in this structure. Okay, so let's try this again. Now, just like always, I'm going to find it easiest with a skeletal structure to go through and put my dots so that I know where the carbons are. And because I'm so interested in the number of hydrogens, I think it will help if you're struggling with chirality, is to take a skeletal and turn it into a condensed. So we're going to try to do that real quick. We've got 1, 2, 3, 4, 5, 6, 7, 8 carbons. That last carbon has a double bonded oxygen. The third one over has a chlorine. And then the one underneath here has a carbon. And then 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 has a carbon. And then the one next to that has 2 carbons coming underneath. Okay, and then I've got to go in and fill in all the hydrogens. Remember, if carbon has 1 bond, it's got 3 hydrogens. 2 bonds has 2 hydrogens. 3 bonds has 1 hydrogen. And I may put that up above. And then 2 hydrogens. We'll fill this in. Okay, now that I've got all those hydrogens shown, I can go through and mark out all the achiral carbons who have more than 1 hydrogen attached. So this one has 3, 2, 2, 3, 3, 2, and 3. Okay, I can also mark out any carbon that has a double bond, so that carbon can't be chiral. And then that leaves me with, I've got 1, 2, 3, 4 options. Okay, so here's where I'm going to grab my pencil. Focus on the far left, that first carbon, and circle the 3 groups that are attached to it. Okay, plus the hydrogen is obviously unique. Now, the issue is that here again, we have a 2 carbon chain long, and so those are not unique. Okay, so that means that this carbon cannot be chiral because you have 2 non-unique groups that are the same. Then I erase my circles and I focus on the next carbon. Okay, and again, I'm going to circle the 3 groups that are attached directly to that carbon. And I can tell that those 3 groups plus the hydrogen making 4 are all unique. This has 1 carbon, this has 1, 2, 3, 4, 5 carbons, and then this group has carbons, chlorines, oxygens, and so all 3 of those are different. Okay, so that carbon is considered chiral. Okay, and then I erase my circles and I move on to the next carbon. So we're looking at this carbon here. It's attached to a chlorine, which is different than the left side, and the left side is different than the right, again, because you have different numbers of carbons, you have an oxygen, those 3 chains are different. Okay, so that means that this carbon is also chiral. Okay, and then I erase and I look at that last carbon. It has a methyl group, an aldehyde, and then a long carbon chain all attached to it, and all are unique, and so that carbon is also chiral. Okay, and so if I erase all of the circles, I'm down to 3 chiral carbons. Okay, but it does make it so much easier if we first remove all the possibilities with the multiple hydrogens and with the double bonds. Okay, so last example. Again, easier if I go through and mark all the carbons. And then if I turn it into a condensed structure. So I'm going to have a 5-carbon ring. Okay, so I've went ahead and filled most of this out. This carbon has 3, which needs 1 more. And then the carbons in most of the ring, they each have 2 bonds. So we're going to add 2 hydrogens to each of those. Except for these 2 carbons, they only need 1 hydrogen because of the 3 bonds. So, first thing is that we mark through all the carbons that have multiple hydrogens, which means that it can't be any of these CH3, the methyl groups, or any of the carbons within the ring that have 2 hydrogens. Okay, so we're down to 3 options. If I look at that top carbon, and I look at what's attached to it, I can already tell that on the left and on the right, I've got 2 CH3 groups that are identical. And so for that reason, they're not unique, and that can't be chiral. Okay, next I'm going to focus on this carbon in the center. Now with a ring structure, and I'm looking at all 3 pieces, I almost want to split this in half on the ring and look at the left-hand side and the right-hand side of that ring. And so those are different, right? Because the top piece is not part of the ring at all. And then when I look at the 2 bottom pieces on the left and right-hand side, one side has a methyl group coming off of it. And so that makes it unique from the left-hand side. Sorry, the right-hand side has a methyl group and the left-hand side does not. So those are indeed 4 unique pieces coming off of that carbon. And so that carbon is chiral. Okay, and then the last carbon that we want to look at is the one that has this methyl group coming off of it. And again, we're going to split that ring down the middle on the left hand and the right hand side, which is kind of a top and bottom piece to it almost. And so again, you see that the top piece here has all these extra carbon chains coming off the ring, and the bottom part of the ring does not have that. So those are 3 unique groups, and therefore that carbon is considered chiral. Okay, so the trick here again, just remember with ring structures that when you're looking at a carbon to decide if it's chiral, you're going to split that ring down the middle, like with this carbon here with the methyl group. We kind of we envision an imaginary line that runs between that ring structure, and then look on either side. Okay, I hope this helps.